Hello, Past Paper Guy here. I'm going to be doing the solutions to the 2021 assessment material from AQA in physics, A level. This one is on waves, electricity fields and their consequences. As with the other two, I'm not going to be showing the questions, so you'll need to download them yourself and print them off as you go along, and that's due to copyright issues. So we're going to start on question 5.1, which is from the June 2020 paper on electricity. And we're given a circuit with 3 bulbs all in parallel, each of which is 1.5 watts. And we have to show that resistance of one of the lamps, when it's operating at 12 volts, is about 100 ohms. So this is, we just need to use an equation like this. You can use P equals IV and V equals IR to get that as well, but this does it all in one step. So R is equal to V squared over P, which is equal to 12 squared over 1.5, which is, when you put that in a calculator, 96 ohms. And it's a show that question, so we've got to make sure that we do it to more decimal places. Initially, the power supply is connected to the lamps using short copper wires of negligible resistance. Calculate the current in the power supply. Again, straightforward question. Use P equals I times by V to calculate the current. So I is equal to P over V, which is going to equal 1.5 divided by 12. And this is in for one lamp. So we have 1.5 divided by 12 gives us an eighth, so 0.125 amps in each lamp, so 3 lamps is equal to 0.375 amps, or 0.38 amps to 2 SF. Question 4.1, this one comes from June 2018. And the first thing that we have is we've got like a wire wrapped around some sort of solid core. So it's wrapping around like that. Now I assume we'll have to ignore the diameter of the wire in this, but we're looking, if we think of the wire being wrapped around like that, then one full lap means that the length of the wire is one full circumference of the circle. So as the wire gets wrapped around, that is the length of the wire. We've got 50 turns, so the length of the wire, which we're going to need, is going to be 50 turns times by the circumference, which is pi d. So that's 50 times by 3.14 times by d, which is 8.0 millimeters. So make sure you get the right units there. So 50 times by 3.14 times by 8 millimeters gives you this length of wire. .256 meters. We're then going to use the resistivity equation. So R is equal to rho L over A, which leads us to A is equal to rho L over R. Well, rho is given in the question, 4.2 times 10 to the minus 7. Then L is what we've just worked out, divided by the resistance, which is meant to be 250 ohms, 0.25 kilo ohms. So we want to times this by 4.2 times 10 to the minus 7. We want to divide everything by 250, and that gives us an answer of 2.11 times 10 to the minus 9, and that's meters squared. So it's quite a thin wire then. The next part is we've got to work out if the resistor choice 4.2 is suitable, and to do that we want to work out the maximum power dissipated in that resistor. So we pick the worst case, So the worst case scenario is if the resistance of the thermistor is almost zero, and at that point all of the potential 9 volts will be across the, so we've got 9 volts here, we've got the resistor that we're looking at, 250 ohms there, we've got the thermistor which is in parallel with something else, and 0 volts there. So if this is almost zero, then all the voltage will be across that there. So let's just work that out. So P is equal to V squared over R, which is equal to 9 squared. So worst case scenario, all the PD is across the 0.25k. So divided by 250, and you put that in your calculator, it comes out as 0.32 watts. Okay, and that is, this is less than the 0.36 watt resistors that the person has bought, so it will be okay. Question 4.3. Well, this one is, we've got this circuit here. We've got 9 volts at the top as the power supply. We've got this resistor here, and we've got this thermistor here. And we're told that this is going to be 750 ohms, this is 250 ohms. This is what we're trying to find out. And we want this voltage across here to be 5 volts, which means that the voltage across here is 4 volts. Now, multiple ways you can do this. So that connects back to that. But the simplest is to break it up into multiple problems. If we work out this current here, then we can find this current here and work out this resistor. The other way you can do this is use a potential divider, that'll give you the resistance of this one, and then you can use resistance in parallel. But it really is significantly easier than that if we just do it this way. So I1 is equal to V over R, and that is equal to the voltage drop across here, which is 4, divided by 250, and that gives you 16 milliamps, I think. So 4 divided by 250, yeah, exactly 16 milliamps. Okay, now we can work out the voltage, the current through the thermistor. So I thermistor is equal to V over R, and the voltage drop across here is 5, and the resistance of the thermistor in the test scenario is 750. So we just do 5 divided by 750 gives us 0, so that's 6.66 milliamps. Just changing it to milliamps there, like that. So the current down this branch here, IR, is equal to this current coming here. Take away the current that goes down that branch, the rest of the current must go that way. So that's Kirchhoff's first law. So we take that away from 0.016. It's negative, but so we get is 0.00933 amps, or 9.33 milliamps. And then we just do R is equal to V over I. So the voltage drop across there is 5 volts. The current through that resistor is 0.00933 ... 5 divided by answer is equal to, ignore the minus sign because I just did these, take away the other way around, 535.7, so that's 540 ohms to SF, and we should give our answer to 2SF because it asks for significant figures and everything in the question is given to 2 significant figures. Question 3.1, this was taken from June 2019. Explain how a stationary wave is produced when the stretched string is plucked. Okay, so we have a string, we pluck it and the string wobbles up and down like this, forming a stationary wave with an antinode in the middle, a node at the end and a node at the other end. Right, so the first thing I think you need to say, plucking the string causes vibrations. Oops, can't spell. It's always been a problem. Which send waves down the string. These, and then let's get a keyword here, don't use something like bounce off, use the keyword reflect off the ends, and now we have waves of the same frequency and similar amplitude travelling in opposite directions. These interfere to make stationary waves. So the way a guitar string actually works or something is you pluck it and most of the frequencies just cancel each other out and make gibberish, but only at certain frequencies establish the stationary waves, and those are the ones that are kept and all of the others just eliminate each other. Right, that's not really enough detail for our 3 marks though. We, for some reason, need to talk about the fact that the ends are nodes. That's in the mark scheme, so let's just do that. So the ends are fixed, so become nodes, and the middle will have areas of constructive interference that become antinodes. Okay, only frequencies which have nodes at the ends become stationary waves. So that corresponding to L, so that's L there, equals to lambda over 2, 3 lambda over 2, 5 lambda over 2, etc. Like that. So the bits that we've got in here, we said what happens when you pluck the string, it causes vibrations. The vibrations reflect off the ends, use the keyword there, don't say bounce off. And then here we've got the definition of a stationary wave. We've got waves of the same frequency with similar amplitudes travelling in opposite directions. So I'll put that in specifically because that's the definition of a stationary wave. They interfere, another key word, to make stationary waves. Question 3.2, we're going to be needing this equation here. And mu is the mass per unit length, which is the mass of 1 meter of the string. So we really just need to bung the equations, and I'm going to do a little bit of rearranging first. And then square everything. So mu is equal to 1 over 4L squared T over F squared. Right, so let's see if we can get this right. So we've got 25 on the top is T divided by, and we've got 4, and the length of the string is 0.33. Sorry, 4 times by 0.33 squared times by the frequency is 370 squared, and hopefully that gives us the answer. So it's 4.192 times 10 to the minus 4 kilograms per meter, which is the answer. Determine the speed at which the waves travel along when it vibrates in the first harmonic. So the first harmonic, you've got to realise that L, the length of the string, which is equal to 0.33, is equal to lambda over 2, because the wave continues on like that. Remember, it's in that position, then later it's in that position. So you've got, that's the bit that we're looking at, that's the other half of the wave that we're not looking at. So that's only half of the wave. So lambda is equal to 0.66 meters. And then we just do V is equal to F lambda, and we've got 370 times by 0.66, which gives you an answer of 244.2 hertz. Sorry, not hertz, meters per second. Which is 240 meters per second to SF. Next one, we need to use the graph that's given, and we need to think of how turning the tuning peg through a distance of, or an angle of 75 degrees changes the tension. It's quite a mean question, because if you don't really know what a violin looks like, then you might not really understand how a tuning peg works. But in cross section, here's the peg, and let's say the string is coming into here. If we turn this through 75 degrees, then we will have stretched the string here an extra distance equaling that arc length there, the 75 degrees from there. Let me draw that a bit bigger. So the string did originally come into there. We're turning the tuning peg, and the string is attached to the tuning peg, so we're turning it through 75 degrees, which means that the arc length there is the extra length of the string, of the violin string. So we need to work out what that arc length there is. The easiest way to do this that I thought was 2 pi over 360 degrees times by 75. That's our angle in radians, and then by definition we times that by r is equal to the length of the arc. So we've got 2 times by pi divided by 360 divided by times by 75, so that's our angle in radians, and then we times it by the diameter of the circular peg is 7.02, so we need to times it by 7.02 divided by 2, and I get that the extension therefore delta L, that's delta L isn't it, the change, is going to equal 4.59, and that was all in millimeters. So if we use the graph and we go up at 4.59 and across, then we're pretty much smack bang on 10 newtons there. So the tension, delta T, the change in tension is 10 newtons, which means that the new tension is going to equal the 25 from before there plus this extra 10, makes 35 newtons. Right, so what's the new frequency? Well, frequency is proportional to the square root of t from that equation there. So if I take the old frequency, 370, and I divide by the square root of the old tension, and then I times it by the square root of the new tension, then we get the new frequency. So F2 is going to equal F1 times by T2 over root T2 over root T1. If you're struggling to follow how I did that, so F2, let's write the answer down and then I'll explain a bit more. 7.7 hertz, dot, dot, dot. So that's 440 hertz to SF. Right, so let me just explain a little bit more detail. I have that F over square root of T is equal to a constant, because they're directly proportional to one another, everything else being the same. So we've got F1 over root T1 is equal to F2 over root T2. I rearrange that equation to get this equation here. So it's the old frequency divided by the square root of the old tension times by the square root of the new tension will give us the new frequency. Question 3.1 comes from June 2019, and the first part of it is just to define the gravitational potential. So it is the energy required per unit mass to move a small positive test mass from infinity to that point. Right, now that's just the definition. You do not need the word positive in there. I always put that in just because then I only have to learn one definition of potential. So for electric potential, you can then just change this per unit charge, and then to move, and that change that to charge, and you're away. But obviously all mass is positive, that we understand. Question 3.2. So this one's it's got some equipotentials like that. Now, if you draw field lines, when you've got equipotentials, you know that they're at 90 degrees to the equipotentials. So that means that these field lines are not parallel, which means that it can't be a uniform field. So the field lines are at 90 degrees to the equipotential, and then I would draw that on the diagram lines. So they are not parallel and so are not uniform. And this question 4 is from June 2019 about electric fields. We have these two spheres and they are repelling one another an angle theta apart, and they move so that they are 40 millimeters apart, and the distance between their centers therefore is 80 millimeters. Right, calculate the potential on one of the spheres. Well, the potential on one of the spheres, we can use Q is equal to CV, rearrange that for V, so we get V is equal to Q over C. So that's going to equal, the value of Q was 52 times 10 to the minus 9, that's 52 nanocoulombs from the question. And then the value of the capacitance, well, it tells you what the capacitance of a sphere is, which is 4 pi epsilon naught times by its radius. And its radius was 20 millimeters, so that's 20 times 10 to the minus 3. So we bung all that in a calculator and we're going to get the answer. And then we divide that by 4 pi. Epsilon naught is 8.85 times 10 to the minus 12 times by 20 minus 3. And there we have 23,370 volts. So 23,000 volts to 2SF. Draw labelled arrows to show the forces on sphere B. So it's just sphere B then. So we need to draw 3 forces. The first force we can draw is the tension there. The weight of the blob has to go from its very centre. And then there's an electrostatic repulsion which you could draw from the middle here. Like that. Suggest a solution to one problem involved in the measuring of D. Well, this is the measurement of D here, the distance between these two. So this is a funnily worded question. They're not allowed. The reason they do this is that he's trying to shove 2 questions into one sentence, because you're only allowed to ask one question. So suggest a solution to one problem. So this question is really saying, suggest one problem and then suggest a solution to it. So you have to say what the problem is in order to get the full marks for this. It's a poorly worded question, to be honest, but let's do it anyway. So one problem. Well, my problem was I thought if measuring this distance d would be difficult, because if ever you spheres themselves, because you might change the charge on them. So bringing a measuring instrument close to the spheres to measure D might change the field and their positions. Okay, so that's the problem. The solution, I thought, was you could put a scale behind it and take a photograph. So put a scale behind the spheres and take a photograph. So we take a photograph, be sure to be straight to avoid parallax error. Okay, or you could even take 2 photographs, one at each side. Take a photograph and read from the photograph, or read D from the photograph. So that would be a potential solution. 4.4 is to use the main equation of electrostatic repulsion, which is this: 1 over 4 pi epsilon naught is 8.85 times 10 to the minus 12. Q is 52 times 10 to the minus 9, and it's the same on both spheres, so we just square it. Now the distance between the spheres is the distance between their centres, which is 80 millimeters. So that's 80 times 10 to the minus 3, and we square that as well. And that gives us 1 divided by 4, brackets, 4 pi times by 8.85 exponent minus 12. So that's that first bit, times by 52 minus 9 squared. And then we need to divide that by 80 to the minus 3 squared, and we're given 3.799 times 10 to the minus 3 Newton, which is approximately equal to 4 times 10 to the minus 3 newtons, which is what they want. Make sure that you always write it down and show your more decimal placed answer. Question 3.1, this one is from the June 2020 paper and it's about interference. Explain why two loudspeakers form a coherent source of sound waves. So they are both connected to the same signal generator. So if they're both connected to the same signal generator, that means that they have the same frequency, not only do they have the same frequency, there's a constant phase difference wherever you are between the signals from both of the speakers. So they have the same frequency and a constant phase difference. And that's the definition of a coherent source. Okay, we now need to explain why, as the speaker there, sound coming out, we start here, we move to here, why we go from a maxima through a minima to a maxima, and this is all about interference. Okay, so here the path lengths from here to here and here to here, so this one's called P and this one's called Q, are the same, which means that they arrive in phase here and are constructively interfering, so we get a maxima, large amplitude, loud sound. As we move to here, we now have different path differences. We've got this one's got to go a little bit longer, this one's got to go a little bit shorter. Now the path difference is half a wavelength out, so they're destructively interfering and we get a quieter sound. And then back to here, we again have a path difference, but instead of the path difference being 0 like it was here, it's now one full wavelength, so the distance here is lambda. So this goes one extra lambda than this does. So that's the same as that, and then we've got one extra lambda. So they both arrive in phase here, and therefore they constructively interfere. Right, so let's try and write that down. At A, the path difference between PA and QA is 0. So the waves are in phase and interfere constructively Right, now I'm going to force this word in here. I wouldn't have used this word, but the mark scheme has picked on the word superpose when they superpose. Now, this is really weird, but he's really insistent that you do not write superimpose. So that is told to mark wrong. It's one of these times when AQA just randomly decide that they want a particular word, and this time it's superpose. Do not write superimpose. There is a subtle difference between these two words. Superimpose means that if you put something on something else, you can see both of them once they're on top of one another. That's what superimposition is. Superposition is when you put one thing on top of the other and they join together to make something new. So that's why this word is superpose. Don't use the word superimpose. For some reason, they're really picky about it on this particular question. So bear that in mind, please. So At A, the path difference between PA and QA is 0. The waves are in phase and interfere constructively when they superpose. Okay, you've got superposition of waves, interference. Here it's constructive interference. As the person moves to B, the path difference changes. This leads to destructive interference and a reduced amplitude, so quieter sound. As they approach B, the phase becomes, phase difference, path difference, sorry, path difference. The path difference becomes one full wavelength, that's lambda. So the waves are in phase again and constructively interfere, leading to high amplitude and a loud noise. Okay, so what did we need to get across in that? We needed the keywords interfere, we need to talk about the phase difference and the path difference. If you can, we want to talk about the constructive, destructive and constructive. So there's the destructive, constructive and constructive. And we want to use this silly word superpose. Do not use superimpose. On to the multi-choice now, question 23, taken from the June 2019 paper on electricity. We have point P here, we've got a resistor there, we've got some current flowing in here, some current flowing in here, and we've got a resistor here, 20 ohms that one, 10 ohms that one, 0 volts there, or ground there, and we want to know what the potential difference is between there and there. So V is equal to I times by R, so the potential difference between here and here is going to be 2 amps times by 10 ohms, which is 20 volts. And then the two currents join together, so we get 6 amps going from here to here. And so we get 120 volts here, 6 amps times by 20 ohms. So the total potential between there and there is 140 volts, which is D. Question 18. We have to work out what these statements about the stationary waves on a rope are. The first harmonic has a wavelength of 2 meters. Well, as with the violin question, we know that's true. Here's the first harmonic. The wavelength is an x, so this is just half of the wavelength is the length of the rope. So that one is true. B, the midpoint of the rope is always stationary for even numbered harmonics. Well, let's try some. That's an even number harmonic, so we've got a node there. Next even number harmonic will be there, and node, yeah. So it's always going to have half of the blobs here and half of the blobs here, so it's always going to be stationary. So that's going to be true. A harmonic of wavelength 0.4 meters can be set up on the rope. Right, let me just extend this one a little bit to make it odd. We've got the 1, 2, 3, 4, 5th harmonic now. So that there is 0.4 meters, and that there is 0.6 meters on the 5th harmonic, and that is one full wavelength. So C is possible. So by process of elimination, D is the correct answer. But why is it false? There are 5 nodes on the 5th harmonic. Well, here's the fifth harmonic. And we've got 1, 2, 3, 4, 5, 6 nodes. There's always one extra node than the harmonic on this particular type of wave, because look, the first harmonic has 2, second harmonic has 3, etc. So that's the one that's wrong. So now we've got question 14, which is taken from the June 2018 paper, and we have L over here, K over here, and we've got a, oops, a little bit of a gap there. We've got a graph of potential against distance. So the mass of L is greater. Now this is the greater mass because look, this is dipping down much steeper here. The gravitational field strength at the surface of L is greater than K. Now this is the steeper slope than this, and the slope there is the gravitational field strength on a potential distance graph. The escape velocity of L is greater than that of K. No, the escape velocity here is much higher. We have the escape velocity there needs that much energy. The escape velocity there needs that much energy. More work must be done moving a mass of 1 kilogram from the surface of K to a distant point, K here to a distant point, so that's the potential, than from the surface of L. It doesn't say to where, but we'll assume that it means to a distant point. So that is definitely D, that's true, because that is smaller than that. Question 15 from the same paper is has got a bunch of wavy lines like so. Now minus 2.0, and it's got various units on the end here, and we've got a point here, and we need to work out which direction the field is going here. So it's got to be perpendicular, so it's going either left or right, and the field, if you think about a planet, the field heads into a planet, doesn't it? Shows which direction the mass goes. So it's always going to a smaller potential. So it's going that way from there to the more negative potential. So that is answer C. 19 now, which is taken from the June 2020 paper. We first of all need to work out what the current is. So it's a constant current, so we can just use Q equals IT. So that's 10 times 10 to the minus 6, that's 10 microamps, times by the 100 milliseconds, times 10 to the minus 3 gives you 1 times 10 to the minus 6 coulombs, so 1 microcoulomb, and then we can just use C equals Q over V, so 1 times 10 to the minus 6 divided by, and V we're told is 5,000. And that gives us 2 times 10 to the minus 10, which is answer A. Question 20 is from the same paper. Now, we have got a parallel plate capacitor, like so, and the amount of work done on the capacitor as we charge it up with a fixed potential is going to be W. We're then moving the plates closer together. Now let's get an equation for work done where voltage is constant. A half CV squared is an equation for the work done on a capacitor. Now V is going to be constant because when we change the plates, the battery will continue to keep the potential difference across the capacitor identical. So that's fixed and that's fixed. So therefore in this case, because the power supply is fixed, because the voltage is fixed, that means that the work done, W, is proportional to C. If we move the plates half the distance towards one another, we're doubling the capacitance. So therefore we'll double the work done on the capacitor, which is answer C. Got another question 20, this one's from June 2019, and we have a 1.0 microfarad capacitor being charged for 20 seconds with a constant current of 10 microamps. So the charge that flows onto the capacitor, Q is equal to I times by T, which is equal to 20 seconds times by the current, which 10 times 10 to the minus 6. So that's equal to 200 times 10 to the minus 6 coulombs. What is the energy transferred to the capacitor? This is a stupid question because it doesn't tell you that the capacitor was discharged to start with. But we're going to have to assume that the capacitor was discharged to start with, otherwise it's just impossible to answer. The energy stored on the capacitor depends on how much charge was already on it. That's the whole point of a capacitor. But here goes. E is equal to a half CV squared, favourite energy on a capacitor equation. So that's equal to a half times by C. We're told that is 1.0 times 10 to the minus 6 times by V squared. Oh, sorry, I haven't worked out what V is. V is equal to Q over C, so that's equal to 200 times 10 to the minus 6 divided by the capacitance, which is 1 times 10 to the minus 6, so that's 200 volts. So that's 200 squared. You put all that in your calculator and you get 2.0 times 10 to the minus 2 joules, which is answer C. And that's the end of the third and final AQA assessment that they've released for 2021. I hope you find this useful. I wish you all the best in your assessments in all of your subjects. And I know you're going through a really difficult time, and I wish you all the best getting to the university or the next stage in your life of your choice. Right, thank you very much for listening.